As noted in the previous video, whenever we approximate or find an approximate solution to a problem, we incur an error, and we have to find, we want to make sure that whatever approximation we are using, it is minimizing some kind of an error. So we said that instead of solving a problem ax equals b, of course, in the case that ax equals b does not have a solution, so instead of doing this, we solve an approximate problem, an approximate related problem, ax hat equals p. And we said that this p is the projection of b. Now, the error E is the error in using B instead of P. So you could say the error is AX minus B, right? The difference between AX and the vector B. So what is in there that's not accounted for? So what kind of a mistake could we make if we used AX instead of B? We want to find ways to minimize this error. So how to solve this system so that the error is minimum? We could look at this from multiple angles. The first angle that we looked at yesterday was geometry. And when we say minimize, we want the length of that vector to be smallest. You see, AX is a vector, B is a vector. These are vectors in Rm, and their difference is another vector in Rm. We can talk about the length or the size of the vector, or we can talk about the size of the error by talking about the length of the vector. So by geometry, it's like this. Imagine you have a plane to represent the column space of A, okay? And you have some vector B like that. So this is your vector B to indicate that B is not in the column space of A. Now, when the question here is, what point in the column space should we take so that the error becomes minimal? So if you take the point that is the orthogonal projection, then this error will be minimal. If you take anything else, all of a sudden, the error is bigger. This is essentially the height of a triangle, if you like. It comes from geometry that the projection onto the space will have the smallest error. So using geometry, that's where we're at. We want that B, we want AX really to be that projection. We want to be using the projection. Now, we can look at the same problem from the algebra perspective, and that's exactly what is most important for us. So by linear algebra, and I hinted to this in the previous video, the vector B, which is in Rm, right? The columns of A have m components because assuming A has m rows, right? A is an m by n matrix. So the columns of A are in Rm. I use this symbol to say it's a subset or a subspace. Okay, so by linear algebra, B is in Rm, and we know that B splits into two vectors, one in the column space of A and another one in the left null space of A. Right? We know that from the fundamental theorem of linear algebra. So for any matrix, this is true. So when you take a vector B that is in Rm, you know that you can split that vector into a portion that is in the column space that would solve our problem, and another portion that is in the left null space, which will be the error. So we have P here and E there. So when we look at this, we know, so we said B splits into a P and an E. So now let's go back. The definition of the error stays the same. The question is, how do we address the error? Do we address it through geometry, through algebra, right? So if I'm going to replace P plus E instead of B and see in what way we can minimize this error. And I realize here we are using E twice. So maybe I'll correct this a little bit and say error. The error of using AX instead of B. It may look a little weird. Why are you subtracting here? Well, you know that AX is not equal to B. So AX is a vector in the column space of A. B is a vector in Rm. Their difference is a vector in Rm. How to make it smallest, right? How to make that difference smallest. When the system AX equals B has a solution, AX is equal to B and the error is 0. When AX equals B does not have a solution, then AX minus B will be some vector in Rm, and we want to find a way to make it the smallest. So choose an X in such a way so as to make this error the smallest. Okay. Now, in this case, in the geometry case, I said just use the projection, and really what we mean by that is find X hat that will give us the projection for P. Now, so that AX hat equals the projection. So use this X hat for X, and you will minimize the error. That's what the geometry situation is telling us to do. Now, by linear algebra, we said B splits into two components, a P and an E. I repeat, that is because the column space and the left null space are orthogonal complements. So they split the space into two parts such that P and E are mutually orthogonal. So when you take their dot product, you get 0. P is in one space, E is in the other. That's what orthogonal complements actually means. So now the error is what? The error here becomes AX minus P plus E. We want to figure out a way to minimize that error. And we said, when I say minimizing, I really mean the length of the vector. So if I look at the length of AX minus P plus E, and for simplicity, I'm going to square it. Why square it? Because otherwise, I can write this square as AX minus P plus E transpose times AX minus P plus E. This is the definition of the length squared or the norm squared. Whereas if I don't have that square, then I'm going to have a square root here, and I'd rather not deal with a square root. Because the length is a positive number, if you minimize the square of that positive number, it's the same as minimizing the square of the length. So the square is just for simplicity of computation. It doesn't matter too much whether you're squaring things or not. Now, I'm going to do a little trick here where I will group AX with P in both of the scenarios, and let's see what happens. So I'm going to write here AX minus P, and then that minus is minus E, that is transposed, and the same on the right-hand side. Now, why did I do this? Because this component is in the column space of A. Remember, P was taken to be in the column space of A, and A times X, no matter what your choice of X is, gives you a linear combination of the columns of A. So this is in the column space of A. B might not be. In fact, B is not if this E is non-zero. If E is 0, then you've minimized everything, or your B was already in the column space. So this part is in the column space. This part is in the left null space. In other words, it's not just P and E that are mutually orthogonal, but rather AX minus P is orthogonal to E. Why is that important? Well, let's do a little bit more algebra here. We have, so I'm going to distribute this transpose and write AX minus P transpose minus E transpose times AX minus P minus E. What am I trying to do? I'm trying to use orthogonality. I want things to be 0 here. So when I open parentheses here, you really do multiplication this by this, then this by that, and then negative E times AX minus P, negative E transpose, and then negative E transpose times negative E. So there are going to be 4 components. So we have AX minus P transpose times AX minus P, then minus AX minus P transpose times E. The minus comes from E. Then another minus E transpose AX minus P. Those are actually the same components, the same quantities. And then we have plus E transpose E. Now, these two things are the same because you have a dot product. So in the dot product, it is possible to switch places. So these are the same thing. But that's less important than the fact that since this component is in the column space and this is in the left null space, we know that this product is 0. And that product and this product, they're the same thing. So this whole thing is just 0 from orthogonality. So we end up with what? We end up with AX minus P transpose times AX minus P. Well, that is just the norm of AX minus P squared. And then we have E transpose E, which is just the norm of E squared. So what we see here is that we could minimize, to minimize this error, so to minimize this error, the question is what kind of P to use, right? We could make this 0. Why could we make this 0 but we cannot touch the error? Or can't touch E? The reason is that we have control over the choice of X. The vector B splits into a P and an E. There we have no control. It just is what it is. However, we get to choose the X. We get to choose what linear combination of the columns of A to take. Well, if we take the linear combination of the columns of A that give us P, then AX minus P will be brought to 0, and it will turn out that the square of the error is minimized at E when we take this E. So the error, the minimum error, is exactly this. So we could make this 0 by taking x hat so that ax hat equals p. Okay, that's the point. We can choose an x, we cannot choose how the vector b splits into a part of the column space and a part into the left null space. So we see that the minimum error is achieved when we take x to be this x hat, and then the error is this e squared. So it's least squares because we're taking squares of the error. That's where it comes from. One could tackle the error, finding a minimum for the error by using calculus. So I'm not going to go into details because I cannot possibly expect all of you to have taken calculus. But essentially, in calculus, you could look at this and ask for the minimum. So how to find the minimum? Well, ax minus b is a vector, but when you take the norm squared, you just get a function with unknowns in x. So x could have 2 components, 5 components, 10 components, it doesn't matter. So you actually have a function in the components of x. So a function with multiple variables. Multivariate calculus is what one would use here. And you find the minimum by taking the derivative and setting it to 0. So minimum when the derivative, well, really the partial derivatives of ax minus b squared equals 0. For those of you who know calculus, you can give this a try just for the fun of it, but you don't have to. This is just to complete the discussion on the multiple ways in which we can look at the error terms. Oftentimes, least square solutions, least square approximations are introduced in many settings where students have not taken linear algebra. And so they will go into this, in my opinion, painful proof of the minimum by looking at derivatives. I think it's much more elegant to look at either the geometry or the linear algebra. This may seem long, but it really isn't, and it's very elegant proof compared to looking at derivatives. But in any case, we know that when we solve the normal equation, A transpose ax hat equal A transpose B, that we get the least squares solution. And by least squares, we mean the solution that minimizes this error, okay? Or rather, the norm squared, the least square error. All right, and that is all for today.